G1. And again, a disclaimer, G1 doesn't have chromosomes, but it's a lot easier to draw chromosomes and picture what happens when you have chromosomes than not. Chromosomes will happen later. So I'm just drawing chromosomes to show you how much genetic material there is. And so here is your key. You've got chromosome 1 from dad, 1 from mom. Excuse me, mom, dad. 2 from mom, 2 from dad. Correct? So that's 2 pairs. We need 23 more pairs. But I'm not drawing all of them. You guys get that? So you've got 2 chromosomes, 4, 6, 8, 10, all the way to 46, the last 2 being sex chromosomes. So the first thing that needs to happen is this. We need to go through S phase. And so when we go through S phase, each one of these chromosomes will make an exact copy of itself. So they will go from chromosomes that are single-stranded. Well, they're not really chromosomes at this point. They'll all condense later on. But so here is dad's chromosome number 1, right? This one, and look, DNA replication, polymerase, topoisomerase, all that stuff. Now we've got its identical sister chromatid held together in the middle by centromere, right? So the pink one, which is dad's or mom's number 1, gets replicated. The teal one gets replicated, held together in the middle, and then finally the red one gets replicated as well, is held in the middle. So how many chromosomes do we have now?
4.
Still 4, but they're different. They're double-sided chromosomes made up of 2 identical sister chromatids. Correct? Okay. So just to refresh your memory here, the red and the teal are both number 2. So the red and the teal, these are homologous chromosomes. They have the same length, right? Same gene location, but they can't be the same because one is from mom and one is from dad. So they can't be the same chromosomes. But each sister chromatid that makes up chromosome is identical. So this is now easy. Let's skip over. So this is now G2. Let's skip over to metaphase. Okay. So metaphase, nucleus is gone. How does this happen? The order completely doesn't matter. None of that matters. As long as we have each chromosome lining up down the middle, like this. Okay. Like so. So each one of the 46 chromosomes lines up down the middle. Okay, and remember also, we also have the microtubules, the spindles. So sister chromatids separate. Do I need to draw that, or can I now just fast forward into the 2 new smaller cells? We okay with that? Right, each side splits, right? And so look what you have. Each cell now will have this. We'll have this. Right? So now each cell has the same exact 4 chromosomes that my original cell had. Right? Remember, for you, plus 42 all the way across. And now what can happen? This cell can now go through S, G1S, G2, M, and keep doing that process. So the main concept here is, aside from knowing what happens in each phases, is that you have 2 cells that are genetically identical to the cell from which they came. The 2 daughter cells are genetically identical to the parent cell. Okay? So this process is why you are here. Right? Upon fertilization, sperm delivers 23 to the egg. Egg already has 23. You now have a zygote, that very first cell that has 23 pairs of chromosomes, or a total of 46. And as soon as that happens, mitosis begins. cell division begins, growing begins, and the cells split into 2, and then 4, and then 8, and then 16, 32, and so forth and so forth. You're born 9 months later, and every single one of your cells has the same exact DNA. If I looked at your DNA from your cheek cell, skin cell, pancreas cell, liver cell, whatever cell you have, the nucleus virtually is identical. The DNA is the same because of this process that makes sure each one of the 3.2 billion base pair gets copied every single time during S phase. Okay? The only thing that changes is throughout your development, certain portions of your DNA are blocked from transcription, certain portions in other cells are not. And so you have that cell specialization, right? Where you go from the embryonic stem cells to cells that are now going to be specialized, do something different. And that's why a blood cell is different from a skin cell, which is different from a fat cell, because they became specialized. But the DNA is exactly the same in every one of your cells. Okay? So now, fast forward to I don't know, 10, 11, 12 years old, when Mother Nature tells you it's time to start making babies.
Okay.
You probably should hold off though. I mean, I'm not going to tell you what to do, but. So now we got to make, you gents, you now have to make sperm cells in your testes. Ladies, you're already born with about 500,000 eggs in each ovary. But this process still has to happen because now during puberty you have to now ovulate an egg, which means an egg has to leave the ovary into the fallopian tube where it may or may not be fertilized. So in order to make a sex cell, you have to start with a cell that you already have. Okay? So every single one of your cells looks like this. Okay? This is every single one of your cells. So prior to puberty, we're just starting with the cell that you have. Now they're special, obviously they're a little different, called spermatogonium, oogonium, depending on whether you're male or female. But anyway, the first process that happens is S phase, where we now have replication of chromosomes. And so what are we gonna have? Teal is dad's 2. Pink is, well, I got pink. Which one? Pink is 1 from mom. So pink makes an exact copy of itself. Red makes an exact copy of itself. Purple, pepper, makes an exact copy. And then teal makes an exact copy. First part is exactly the same. How many chromosomes do we have now? 4. Do I have mom's and dad's chromosome in the same cell? Right? Both mom's 1 and dad's 1 in the same cell, correct? Both mom's 2 and dad's 2. All the way down to 23. Okay? But what happens here? And this is the key part. This is what distinguishes you from understanding this part of stuff or not. So I'll draw this and then we'll pick up with this tomorrow, but let me first explain it. Metaphase. The cell is going to split, which means we got to go through the stages of mitosis. So metaphase is going to look completely different. And here's what metaphase looks like. Okay? Instead of these chromosomes lining up on top of each other like they do up here, these homologs find each other. Okay? Chromosome 1 finds the other chromosome 1. So the replicated chromosome 1 from mom finds the other chromosome 1 that is replicated from dad. Remember, they are called homologous chromosomes. They're the same chromosomes in the sense that they have the same length, same gene location, but one's from mom, one's from dad, so they're different. Okay? So, and the order doesn't matter. It's not like they go 1, 2, 3, 4, 5, 6 all the way down. It doesn't matter. The top chromosome could be chromosome 17, right? So to kind of demonstrate that, let's start with 2. So mom's chromosome and dad's chromosome 1 and 2 will line up next to each other. So here is that, and what's the other one? Teal. Okay. So take a look. This is chromosome 2 from mom and 2 from dad. Okay, see that? They have to be next to each other. You cannot have chromosome 1 from dad and chromosome 17 from mom. Okay? 1 from mom, 1 from dad. 18 from dad, 18 from mom. Okay? Now let me illustrate this point again. If the bell rings, give me 20 seconds. Which chromosome is on the left? Dad's or mom's? Mom's chromosome. So let's, for the other pair, let's put dad's chromosome on this side.
So is it all random?
Yeah. And so I'm going to show you why that matters in just a second. Which one am I missing? Pink, right?
Pink.
Okay. So whether mom's or dad's chromosome is on the left or on the right is a complete matter of chance. What you're going to see tomorrow, don't do this yet, but I want you to understand why this was important in just a second. We're going to split this down the middle. Okay? And so each cell is going to get one representative of each pair. Does that make sense? But how many chromosomes from moms or dads each cell gets is completely random. So what I'm basically saying to you is the chances of mom's chromosomes lining up down one side and dad's chromosome lining up on the other side, the chances of that are 1/2 to the 23rd power. Right? It's like flipping a coin and landing on heads 23 times in a row. It will never happen. So here's the first reason, and again, give me 20 seconds if the bell rings. Here's the first reason why every single cell that you make through puberty is going to be different genetically, because you have no control, this is completely random, on which side of the cell chromosome moms and dads go. If we have, take a look, 10 of moms on this side and 13 of dads, this cell will have 10 and 13. The other cell, therefore, by default, will have 13 and 10, which means that cell and this cell are not genetically different. Are genetically different. And that's why siblings will never look the same, right? Because, well, that's one of the first of 3 reasons why siblings will look the same. We'll start with the second reason tomorrow.